Hello, my name is Neil. I work at the University of Colorado, Boulder, as a full stack developer in the chemical and biological engineering department. And I'm going to be talking about scientific computing with Ruby. What is scientific computing? Scientific computing is the use of computational methods and numerical algorithms to model, simulate, and analyze physical, biological, and engineering systems. I'll give an example here. We'll start with a simple example. I have a chemical engineering background. That's the degree I graduated with. And in chemical engineering, one method that we use for producing products is called a batch reactor. Now, on the left, we have a little diagram of a batch reactor, and the way that it works is you dump in your chemicals, which are typically a liquid or a solid dissolved in a liquid. Um, and then if it's an exothermic reaction, you'll stir it and cool it down using a cooling jacket. If it's an endothermic reaction, you'll stir it and heat it up to prevent it from getting too cold and driving the reaction to completion. Um, so we're going to look at the kinetics of a chemical reaction in which chemical A is converted to chemical B in a batch reactor, and then it decomposes into chemical C. This is called a reaction in series, and these two constants, Ka and Kb, are constants for the rate of the reaction, and we'll see how that comes into play here soon. This is a diagram of the behavior of the system in a batch reactor for that reaction that I just talked about. Um, we start with a high concentration of chemical A, and as it is depleted, chemical B is formed. And then as the concentration of chemical B goes up, it starts forming chemical C, and then chemical B is depleted as it is converted into chemical C. And over a long enough time frame, you will have only chemical C, after which you remove it from the batch reactor and purify it and sell it. The defining differential equations for this system are given here. This first one is the changing concentration of chemical A over time. In other words, dCA dt. And it is negative because chemical A is being depleted. It goes down over time. Um, and the rate that it is depleted at is proportional times the rate constant Ka times the concentration of chemical A. Uh, dCB dt, the rate is proportional to a positive value here for as chemical A is converted, or sorry, the higher the concentration of chemical A, the higher that uh, chemical B will be created. So uh, it's basically a mass balance where you'll have a negative term here as chemical A is depleted, chemical A is created, and that's that first term. And then chemical B is depleted, this negative term, and turned into chemical C, which is this positive term here. And then the rate constants are dependent on temperature here. So the reason I talk about these equations is because you need some sort of mathematical model in order to do a simulation. This is the code for the equations that I just talked about. On the right here is the equation, um, and on the left is the code or the method for that equation. Ka takes an argument of temperature. Everything else is a constant. Kb also takes an argument of temperature. dCA dt takes an argument of temperature and concentration. Temperature is passed into Ka, and then concentration is a variable that will change over time. And similar thing for dCb dt, it's dependent on the concentration of A and B as well as temperature. And then dCc dt is just dependent on temperature and the concentration of B. So we're just defining a few methods here that will be used in the actual simulation, which I'll show on the next slide. This is what the simulation would actually look like. Um, Here you start with an initial concentration of A, B, and C, and you start at time 0. And then we initialize an array in which the first element in the array shows the time, concentration of A, B, and C. The time step that we'll be incrementing in is 0.1 seconds. And then while time is less than our max time, in this case 100 seconds, we change the concentration of A by dCA dt, and pass in the temperature and concentration of A and multiply that times the time step. We do the same thing for B and C, then increment time by the time step, add those values to our concentrations array, and repeat. And at the end, we return the concentrations. And what this will look like is an array of 1,000 elements because we have 100 seconds at a time step of 0.1 seconds. So there's 1,000 elements in this array, and each element has the time concentration of each element. Then you can use this in order to create a plot like this. So that's a simple simulation that would be used to, for example, determine how long you need a batch reactor to be operational before you can remove and purify the product. But that's boring. So let's look at something we can play with, because simulations are much more fun when they're interactive. Here I have a simulation in Ruby of fluid flowing around a sphere. I use the Gosu library, which is for drawing two-dimensional graphics. And so I'll just start it up here. And this meeting bar is in my way. There we go. So right now we have water with a viscosity of 8.9 times 10 to the negative fourth Pascal seconds. That's the viscosity, the dynamic viscosity of water. And it's flowing at 0.1 millimeters per second. So around a sphere of 1 meter. Now, that's very, very slow flow, but you'll notice that the water is kind of just moving around the sphere smoothly, which is expected, right? But using the up arrow, we can increase the velocity of the water. And around when we get to one millimeter per second, we start seeing eddy currents. And these eddy currents are created by low pressure systems behind the sphere. And as a result, you get water actually flowing backwards towards the direction of flow behind the sphere. And I'll increase the velocity to around 0.1 meters per second, so 10 centimeters per second. And then with the left and right arrow, we can adjust the viscosity. So the viscosity of honey, for example, is about 10 pascals per second, or 100,000 times that of water. So I'm going to increase viscosity to 10 Pascal seconds. This will just take a moment. And we can see that a fluid with very high viscosity does not create those eddy currents. So Uh, yeah, that's a little demonstration of fluid dynamics. One thing that you will notice is that if you increase velocity high enough, if we go to 10 meters per second, for example, we start to see those eddy currents show up again. And keep in mind that like this is honey flowing at about 22 miles an hour around a sphere of 1 meter. So this would create a ton of force on the sphere, and it's a little bit unrealistic. But um, here you can see the uh, relationship between velocity, viscosity, and the formation of eddy currents behind a sphere. And so, yeah, fluid dynamics are kind of fun, especially when you can play with it and adjust different things. And I just took a couple hours to make this. This is assuming it's just laminar flow, which is basically smooth flow. Um, but this Gosu library is it's really cool to work with, and I'll just show you around how this is working. So, Gosu uses a class called window, which creates a window on the screen, and we can create it with a certain width and height, in this case, 900 by 900 pixels. And in the initialize function, we define a few instance variables. And then what's actually happening is the draw function here is being called 60 times per second. So this draw rect is drawing a rectangle, a gray rectangle, which is the background. And if you go back here, you can see the background is gray. That's just a, a rectangle that's the width and height of the window. Then we draw the sphere. The sphere is actually um, it's a bunch of triangles shaped like a sphere. So like a bunch of slices of pie, basically, because Gosu doesn't actually have an ellipse or circle method for drawing. So I had to make the sphere out of a bunch of triangles. And then we draw the vector field and finally the text overlay, which is the text in the top left. The update function handles events such as pressing the keyboard up arrow, down arrow, right arrow, and left arrow. And all we're doing there is multiplying this instance variable velocity by 1.01 or dividing by 1.01 with a floor of a very low value. We end up dividing by 0 if this gets to 0 and it crashes. So we need a minimum value for um, viscosity and velocity that it won't go below. The math is all down here, and these equations are taken from a paper written in the 70s or 60s, March of 1967, that describes fluid flow around a sphere. So they also provide some experimental data that is what these numbers are for. I think I actually made a JavaScript version of this simulation a few years ago, and um, the way that I made this was telling ChatGPT to convert my JavaScript simulation into Ruby, and uh, and then going and modifying things and getting it to work properly. But I believe someone implemented a numerical version of this paper using like C or C++ plus plus or something, and then I figured out how to write it in JavaScript, and now it's converted to Ruby. But this particular simulation is the calculations are simple enough that or computationally simple enough that we can easily run on one thread and it will be plenty performant. However, um, there are plenty of simulations which are going to require parallel computing, and that's where something like reactor or the parallel library in Ruby, the parallel gem, um, come in handy. While I was preparing this presentation, I made the Mandelbrot set, which is a fractal, and this does use parallel computing because what's happening in this graphic in this simulation is it's actually computing a color value for every single pixel, and it's I think a width of 800 pixels and a height of 600 pixels, so that's like what 48,000 pixels that have to be computed, and each one of them iterates up to 100 times. That's a lot of computations, and that's where something like parallel computing can come in very handy. But um, I made this simulation so that you could zoom in with the idea of being able to zoom in like infinitely far, and you could be able to explore the fractals. But unfortunately, even with parallel computing, it wasn't as performant as I had liked. Um, in an ideal scenario, you would have a frame rate that's more like 30 or 60 frames per second, and it would look something like this. But I believe the HTML5 canvas, which is what we're viewing right now, is a lot more optimized than this Gosu library. And so I couldn't get the performance I was looking for on that one. But yeah, I'll quickly run through the Mandelbrot codes. Most of it is very similar to the fluid dynamics code that I showed before. The exception being that we are using reactor here for parallel computing. And all you do is pass in, you use the etc. library, which is built into Ruby to find the number of processors on your computer. And then we use one reactor for each processor. And then it will, for each row in the image, it will it will use a different processor. So it's basically doing 8 rows at a time for this computation as opposed to 1 row at a time. And that would result in a little under 8 times the performance that you would get normally. So yeah, that would be really helpful using reactor if we were doing a computational fluid dynamics simulation in 3 dimensions. However, mine was in just 2 dimensions. But yeah, that's a little dive into scientific computing with Ruby. So thank you for viewing my presentation. And again, my name is Neil. And yeah, the source code for this is available on GitHub. I'll find it real quick. Uh, so the URL is github.com/neil_the seal/ruby_simulation_examples. And to run this, all you'll need to do is a bundle install, and it'll install all the dependencies. And then you can do a Ruby Mandelbrot, Ruby series, or Ruby streamlines.rb. So thanks again. Bye bye.